Okay, this is my title. Thanks for coming to my talk. So let's start by review some basic facts in group theory. So our G, this G will be a reductive group over complex numbers. So for instance, GON, SON, SON. So this little g is the algebra of this big G. So recall it's the vector space of lambda G invariant vector fields on this Lie group G. So in particular, the element inside this Lie algebra is a derivative on G. And as derivatives, you can define the Lie bracket, which is just the commutator, UV minus VU. And you can verify its still lambda G invariant. In particular, it's an element inside this Lie algebra. So this operation, this Lie bracket, it's anti-symmetric. It satisfies the Jacobi identity. So it's indeed a Lie algebra. So here's some examples. So in the GON case, your Lie algebra is just a matrix. And for SON, it's the vector space of those matrices with trace 0, and SON, it contains those anti-symmetric matrices. So in group theory, people care about representations of something. So let's start from the easiest case, the abelian category of complex representations of this G, of this reductive group G. So this category, its structure is very easy. So this category is semi-simple. It means any objects can be written as a direct sum of simple objects. Moreover, we know all the simple objects. So the simple objects are given by real modules, so-called V lambda check. Here, lambda check is a dominant weight. So a weight is just a multiplicative character of a fixed maximal torus inside G. So for GON, you can choose the maximal torus to be just diagonal matrices. So a dominant weight means the weight is large enough in some sense. You need to choose up a real to define this notion. But if you don't know that, it's okay. So just large enough. So this is the story for this group G. It's well studied and it's safe to say people know everything about it. So, but this category, the representations of the Lie algebra is much more complicated. So recall a representation of the Lie algebra is just an action of this Lie algebra on your vector space such that the commutator of your action is given by the action of the Lie bracket. So it's this formula. So the structure of this category is more complicated. So, and the previous semi-simple category is a full sub of this thing. So I'm not going to tell you something about any questions. I'm not going to tell you anything about the structure of this G mod. Instead, I want to tell you a story about deformations of the above picture. So I will explain why people want to deform this data, but now let's look into deformations. So a deformation of the previous category, so it's a continuous family of categories whose fiber at some point is group G or G mod, but the fibers at other points are different. So if you want to deform this category, so the easiest guess is to deform the group G or the algebra little g, but actually you cannot do this. So these things are classified by discrete data known as root data or root system. And since they are discrete, so there's only trivial deformation. However, you can deform the universal enveloping algebra UG of this the algebra G. So recall this is an associative algebra whose left modules, whose category of left modules for it is equivalent to the category of representations for the algebra. Therefore, passing from this the algebra to the universal envelope loses no information. So now our goal is to deform this algebra. And this deformation can be made by using very explicit construction. So I will not write down the formula, so I just explain the ideas for this deformation. So this UG has some canonical generators called Chevannet generators and subject to Chevannet relations. So then for each non-zero complex number, so there's something called loose quantum group, which is actually an associative algebra. So it has similar generators subject to similar relations called quantum Chevannet relations. actually I'm lying here. So if you are expert, you will realize I'm lying. But yeah, I just want to give you the rough idea about this. So when Q is 1, so you can recover the universal envelope algebra of this Lie algebra. So I also need to say that this family moves continuously when your Q changes. So it's indeed a deformation. So once you have the deformation of the algebra, you can consider this category. So the net modules for this algebra, and inside this large category, so there's something that there's a smaller category called RepQG, the representations of the B quantum group. So it just contains modules satisfying certain conditions, certain integrability conditions. So this is the desired deformation category of RepG. So, and as before, so you can define quantum well modules. Oh, I forgot to mention that the original well modules can be defined using some induction from Borel's. Here, the quantum well modules can also be defined using some induction, but from some quantum Borel's. So you can define these modules. So these quantum well modules are deformations of the original well modules. However, so these modules are not are no longer simple when your Q is a root of unity. And in that case, the structure of this category is much more complicated. So for instance, I think people don't know how to calculate the extension groups between these quantum well modules. So you may wonder, so since the set of root of unity is just a zero measure set in all complex numbers, you may wonder why people care about this special case. But in fact, it is this special case that attract most interest. For instance, it's analog to what's happening in the theory of modular representations in positive characteristics. And these are things that people care about. So really, the quantum phenomenon is mostly interesting in the root of unity case. Okay, so people don't know how to calculate these things, but sometimes in math, we can use one unknown to explain another unknown things. And I'm about to tell you another deformation of this RepG, this time using affine algebras. So you consider this tensor product. So you just change your coefficient field from C to the field of Laurent series. So it's the so-called loop Lie algebra. And you consider a central extension of this loop Lie algebra by C. So by central, I mean this C is in the center of the Lie algebra. It means the Lie bracket of elements in it with any other element is 0. And it is known that such central extensions are classified by non-degenerate, certain non-degenerate forms, binary forms on the Lie algebra. So again, I'm lying here. So you need to assume G to be semi-simple to have this, but just have the general feeling. So this kappa, therefore, this binary form is unique up to a scalar C, a non-zero scalar. And for each such non-zero scalar, we can consider this category. It's the representations of this central extension. And inside it, so there's a smaller category called Castanucci category. So you set its object satisfies certain conditions. So let me say it in words. So you require this C, the center acts by scalar multiplication, and you require modules to be integrable for the arc group. So it's just some small category. Okay, so now it will be a deformation of RepG that satisfies similar properties as the previous quantum deformation. So in particular, you can define affine well modules. So by using induction, and they are labeled by dominant weights. And this time, when C is rational, so this affine well modules is not simple. And in that case, the structure of this category is very complicated. And again, we don't know how to calculate the extension groups. So I guess people can already guess what would be the next page. Let me just show you. So it's a theorem by Castanucci. So it says if Q is the exponential of C inverse, and if C is nice enough, so then there's a certain equivalence from the quantum deformation to the affine deformation. So that sends the quantum real modules to affine real modules. So you may wonder why I require C to be negative. So it's for this reason the C is positive. So there's an equivalence, but only for derived categories. It's only for negative C that is an equivalence between abelian categories. So you might notice that there's a negative 1/2 shift here. So it has some deep meaning, but I'm not about to explain it. Instead, I want to explain the word braided monoidal. It means this equivalence, the Castanucci equivalence, is not just an equivalence between categories, it's an equivalence between more structures. So recall a monoidal category is just say abelian category equipped with a tensor product. So you can view it as an associative algebra in the category of categories. So then a braided monoidal category is a monoidal category equipped with some braiding isomorphisms from X tensor Y to Y tensor X. But here's a warning. So being braided monoidal does not mean so the C is commutative. So to have the commutativity, you need to require the gamma XY and gamma YX to be inverse to each other. But in the definition of braided monoidal category, you do not require them. So instead, braided monoidal categories should be viewed as categories equipped with two commuting monoidal operations. So it is a fun exercise to see indeed these things are the same, but I will not show you here. So and since you have two commuting monoidal operations, these things are known as E2 categories. But actually I'm lying here, so just give you some feeling about this. So now let's look at the braided monoidal structure of RepQG. So this is given by pure algebraic method. So the monoidal structure, the tensor product is given by a hopeful algebra structure on the algebra. So recall this means instead of the more than the multiplication, you also have a co-multiplication, this delta. So subject to certain conditions. And this allows you to define the notion of diagonal actions on the tensor product of two modules. So this gives you the monoidal structure. And the braided monoidal structure, the braiding isomorphisms are provided by, if you online the definition, so these are provided by isomorphism. So here this T is just switching the two factors. So again, so for this you can lose, so both this delta and this isomorphisms are given by very explicit formula. So for instance, you can Google just a matrix and you can see it. So on the other hand, the braided monoidal structure on the affine side is defined using a different method. So this braided monoidal structure really has a different flavor. So to see it, so to forget functor from this Castanucci category to the underlying vector space is not even monoidal. So instead, the monoidal operation is called fusion. So and it is defined using some geometric and analytic methods. So which I will not show you in this talk. Instead, I want to explain in my favorite way what is the fusion product. So by using the factorization structure on the Castanucci category, or in fact, the derived category of it. So roughly speaking, a factorization structure for this thing is a family of categories on this A2, so whose fiber at the diagonal is just your derived category, and fiber away from diagonal is the square of your category. And imagine that picture. So now for every direction that approaching your diagonal from points away from the diagonal. So there's a construction called nearby cycles or taking limit constructions so that you can define a functor. So from the tensor product to the category itself. And since there are essentially only two directions that allows you to approach the diagonal, so you get two monoidal operations, and this gives you an E2 structure. Well, but again, I'm lying, so this is just a feeling about this. Okay, so this finishes the introduction of the Castanudsky equivalence and the braided monodal structures for this equivalence. Now I'm about to say something about my research work. So it's a work by Lin Chen and me. So the actual paper will be posted on arXiv very soon. So in fact, this is not my thesis work. This is my recent work. So let's go back to the basics of RIP theory. So recall we reviewed this RIP G and G mod, and between them there's a category called GB mod for the Harris-Chandler pair. So its objects are just modules that satisfying some weaker conditions. So the structure of this category is richer than RIP G, but it's still within reach. So, and it is known as the BGG category O. So BGG is for Bernstein, Gelfand, and Gelfand. So then people can define deformations of this BGG category O. So using both the quantum method and the affine method. Let's call it just the quantum category O and the affine category O. So I will not give you the definition here. But just give you a general feeling about these things. Okay, now here's the theorem. So by Lin Chen and me. So originally conjectured by our advisor, Dennis Gatesbury. It says there's a derived equivalence from the quantum category O to the affine category O. And again, this equivalence would send some standard generators to standard generators, but I will not tell you what are those generators. So if you note some words, the generators on the affine side are Makimoto modules, and on the quantum side are the affine Verma modules. So it is a derived equivalence and it is not T-exact. So even when C is negative, it's still not T-exact. And we don't think it's of bounded cohomology amplitude. So the proof, our proof used geometric methods, so or algebraic geometry method. So we realize both sides has the category of factorization modules for some factorization algebras of the configuration space. So note that I didn't say it's a braided monoidal equivalence because so far we don't know. The reason is the following. So on the quantum side, so there's indeed a braided monoidal structure. So defined similar to the RIP-QG case. So you can use R matrix to define it. But on the affine side, so now a priori people don't have a braided monoidal structure on it because the affine category O is defined by using Iwahori subgroup. So an Iwahori subgroup does not factorize. However, so there are some models for this derived category. By models, I mean some other categories equivalent to it that does factorize. And therefore, these models have chance to have braided monoidal structures. And we are exploring whether we can show that this equivalence would match these braided monoidal structures. Also, I don't have time, but I want to say that so this is just not just an abstract equivalence, so it can match many operations on quantum side and on affine side. For instance, on the quantum side, there's an operation called semi-infinite cohomology. So it's a generalization. Or on the affine side, there's a thing called semi-infinite cohomology. And on the quantum side, there's a thing called quantum cohomology, and these things would match. So it's more than just an equivalence. So I think I want to finish here. So thank you for your attention.
Questions? What does that mean? Oh, sorry. Please go ahead.
I mean, again, you gave these examples of equivalences. Is there something that you can, do you have an example of something that, or some calculation or something that you can do on one side that it's much easier to do on one side than on the other side? Like, I guess I'm trying to ask, like, what's the benefit of having this equivalence?
Certainly. So let's look back to the equivalence or even to the Casanutic thing. So these two categories, so since they are defined using different methods, so there are different, so let me say like this. So this quantum side, so there's some topological way to study it, like using some breeding. And this affine side, you can use some algebraic geometry way to study it, like the localization thing. You can localize it to the category of D modules on something. And such an equivalence would allow you to translate some problems about the quantum group to some problem about the Casanutic category, and further to something about geometry. By geometry, I mean something on, say, finite variety and the Broughard cells of it, and you have much more methods to study them. And there are indeed some results that can be proven, so by translating a problem to the other side. So for instance, as I said, so where's our equivalence? Yeah. Let me say it in words. So on the quantum side, so since things are essentially built from finite dimensional case, so you have many constructions. Like you can construct some what's the name? So I think it's called BGG resolutions for some quantum real modules, and this can be translated to the affine side, and a priori, so the construction of these things are hard. Also, for instance, on the quantum side, so in the literature, people prove some vanishing results for the quantum cohomology using some methods calculation. So they assumed some, for instance, something to be even, and for the odd case, they cannot do it. But once we have the equivalence, we can use some method to prove it on the affine side. So it really allows you to translate the problem on the one side to other side. Does it answer your question?
I think. Yeah. So is the quantum cohomology that you just said anything similar to the quantum cohomology?
By quantum cohomology, I mean the quantum cohomology for the nilpotent radical, for the upper nilpotent radical. So you start from representation for ReP2G, you're doing cohomology for UQN. N is the nilpotent radical.
I was going to ask, what is the meaning of nice in your theorem?
Okay, nice. Okay, so nice in the Casanutic case, it means admissible. So it's a notion. So it just means either the C is irrational or C is rational, but the thing on the top is larger than a number on the only depends on G. So it's just yeah.
And the same in your
yes, the same condition in our theory. So it's the requirement so that the Kashiwara-Tanizaki localization theorem can work.
Okay, if there are no more questions, let us thank